So if we keep on this hydrogen example, what we showed is that when a covalent bond forms, we actually get a release of energy, right? And that should make sense because the release, this is the negative 436 kilojoules per mole. So we're releasing energy from the system. We're going from a high energy state to a low energy state, right? Where if this is the energy curve here, we're starting here at H plus H, and we're ending up down here as a bound H. That's the direction that we're moving to form this stable covalent bond. And we should think about this as a sort of reversible system. So once the bond is formed, we're at this lower energy place. So if we want to break that bond, we have to retraverse this energy curve back uphill to separate these atoms from the original bond. And it's going to take exactly equal and opposite energy that you released to affect that process, in which case you have to put in 436 kilojoules per mole to get this to break. We call this, and we've already referred to this when we talked about Born-Haber cycles, we call this the bond dissociation energy. So the bond dissociation energy is equal and opposite to the energy that you get from forming the covalent bond. In other words, it's the energy that you got to put into the system to go back from the stable place to the less stable place to break that bond apart. Bond dissociation energies, they're always positive, which means that you always have to put energy into the system. You're always going uphill, positive, from a stable state to a less stable state to get that covalent bond to break. The nature of the actual covalent bond dictates how strong that bond is, or in other words, how large that bond dissociation energy is. And you can imagine molecules that contain various bonds, whether it's a carbon-hydrogen bond or a carbon-carbon bond. There's going to be other exterior forces in that molecule that might change the exact bond dissociation energy for that specific molecule. So in that case, we use average bond dissociation energies. So in other words, the carbon-carbon bond in, say, this molecule, which would be ethane, this might be slightly different than a molecule that is very similar, but instead of that hydrogen there, we put an OH group, that's methanol. So this bond here is the same carbon-carbon bond that's showing up here, but this table is giving us an average value, and that's averaged over all the possible types of chemical environments that that carbon-carbon bond could be established within. And so you can get a sense, looking at this table, how bonds can be dramatically different in strength. And so look at the hydrogen-hydrogen bond. That's for the hydrogen molecule. That's pretty large. It takes 436 kilojoules per mole to sever that bond. Similarly, a carbon-hydrogen bond takes 410. What else is interesting here? So carbon-carbon, 350. In this case, we can get really sort of small with these big, the larger the atomic radius, the smaller that bond energy is, meaning it's easier to break apart because they're further away from each other. So that brings us to the relationship between bond length and bond strength. And so if you look at this table, this is just collecting 4 different types of bonds, the HF, HCl, HBr, and HI. So these are all group 7A bound to hydrogen. So these are the halogens. If you look at the bond dissociation energy, you can sort of see a trend, right? Let me pause this for a second, grab a periodic. If we look at the periodic table here, we're looking at these halogens here, this group 7A. what we can see is we already know that the atomic radius gets bigger as we move down the table or down a group, and that's just because you're packing in a whole bunch of protons, right? You're going from 9 protons to 17 to 35 to 53. You get a way larger nucleus. You got a bunch more protons and neutrons jammed in there, and you also have a whole bunch of bigger electron shells in the configuration, right? So as that radius gets bigger, and we go down the group here, that radius gets bigger. The bond length then also gets larger, right? Because you're talking about say H F versus, let's just say that these aren't to scale clearly, but I'm just giving you a sense, versus H I, we have totally different bond lengths between these that are just dictated by the size of the radius itself. So as these two things get further away from each other, as that bond length gets farther and farther, that attraction between the positive center of the nucleus or nuclei and their electron clouds, it gets weaker and weaker and weaker. In other words, what we see is that bond strength gets weaker as this radius gets larger, or the bond length gets larger. So these two are inverse to each other. So bond length is increasing down the table or down the group because the iodide gets larger, but at the same time that gives you a significantly weaker bond just because they're held together with a smaller or less intense attractive force. So with covalent bonds, we can actually have more than one bond form between two different atoms. And so what I'm showing you here are a variety of different bonds, their lengths and their strengths, just based on the differences in how many bonds are formed. When we talk about multiple bonds, let me write here, multiple bonds, all that means is each bond, so each time we have a line drawn between something, we'll say this is oxygen, that signifies 2 electrons that are being shared, I could write them like this, between that. So if we have then, in contrast, oxygen that looks like this, what that means is we've got 2 sets or 2 pairs of electrons that are being covalently shared between them. As you get more electrons that share between them, then those atoms get closer and closer together. They get drawn in. That attractive force is pulling these two things closer and closer to each other. And so in the case of nitrogen, you can actually get 3 bonds that form, which means there's 6 electrons here. Those are really tightly pulled towards each other. And that's reflected here. If we look at the bond length of oxygen gas, this is the stuff you breathe, that's 121 picometers. But then we look at nitrogen and it's 110, just based on the fact that these are a double versus triple bond. And that bond length and strength, that inverse relationship holds true here as well. So as that length gets smaller for nitrogen, look at what happens to its strength. So the strength of an oxygen bond is about 500 kilojoules per mole, but the strength of a nitrogen bond is almost double that. So it's this huge, huge increase in bond energy. In other words, it's a lot easier for us to break apart oxygen in the air, which our bodies do all the time. That's why we respire. That's part of our metabolism. But it's almost impossible, and actually it is impossible for us to break this nitrogen bond. And this is what we require plants to do. This is what we call nitrogen fixation. Humans don't have the machinery, the chemical machinery, to actually break this bond. But we do have the chemical machinery to break this bond. It's a little bit weaker though. You can look at this molecule here in contrast to oxygen. So this is oxygen bound again to itself. So this is a really good direct comparison. Oxygen versus this is hydrogen peroxide. We talked about this earlier. And so the single bond, much larger than the double bond. Because this is larger, that means the bond strength gets quite a bit smaller. The same can be done in a side-by-side comparison here between nitrogen And this compound here, where we're comparing a triple bond to a single bond with nitrogen, gets a lot bigger, and in doing so, the strength decreases significantly from 945 to 275. So this is a much easier bond to break compared to that triple bond. One additional concept that I want to introduce, which is going to come back to us in the next chapter, is this idea of bond order. It's really not a new concept, it's just a different way to account for single, double, or triple bonds. So when we're talking about bond order, it's the number of pairs of electrons that are shared between atoms. And so it's just it's sort of a shorthand way to talk about the number of bonds. So in the case that I have sort of here, the bond order here for this oxygen with just one pair would be a bond order of 1. This double bond here would then be a bond order of 2, and this triple bond here would be a bond order of 3. We're going to add a little bit of complexity to this in chapter 7 and account for what we call non-bonding electrons. But in this case, we're just sort of introducing it just generally. And so another way to think about this is as the bond order, I'll just write this as BO, is that increases, then the strength of that bond also increases, which is what we saw in this example here, and the length decreases. Those things get closer and closer together. So the closer the atoms are, because they're sharing more bonds, then it's a stronger bond. So this is a good sort of general relationship that we want to commit to memory here and be able to employ and rationalize later.